this can give me my I in the S domain, or this is basically S in the S domain. And you can find the, you can take the inverse Laplace transform to find the time domain response. Okay, so while we're here, let's just look at one of the application of going into the frequency domain. So if you look at this one, this transfer function is 1 over 1 plus j omega RC, right? What is the value of this transfer function at omega equal to 0? If I put omega equal to 0, this term would be 0. So the transfer function is going to be just 1 over 1. If omega is increased up like to infinity, moves towards infinity, right? Then we have a very huge denominator, so the transfer function is going to be equal to 0, right? So we basically know that this system is a system that omega, if I look at the transfer function, I'm looking at the magnitude basically. It's gonna pass the low frequencies, but as omega moves to higher frequencies, it basically, the transfer function, the magnitude of transfer function moves towards 0. Okay, so this is a system that basically passes the low frequencies but reduces the high frequencies, mitigates the high frequency. So this is, if we look at this one, this is a low pass filter. Okay, where if you look at this one, so if you actually choose voltage of the resistance as your output, then in this case, this is what we have, j omega RC, 1 plus j omega RC. So if omega is equal to 0, the transfer function is 0. Sorry. If omega moves to infinity, right, basically you can ignore this term, and your transfer function, it's going to be 1. So in this case, we have the opposite, right? This is a system, this is a transfer function that would basically doesn't let low frequencies to pass, but for the high frequencies, the magnitude of transfer function is almost 1. So this is like a high pass filter. So this is a high pass filter. So that's one of the advantages of moving to frequency domain. We're gonna see what kind of filter we need, and what happens to certain frequencies when we have a system. But while we're here, I want to solve like one problem from beginning to end. Excuse me. Okay, sorry about that. So let's say that we don't know anything about this circuit. We only have the transfer function, and we want to know what's the output when we define the output as the voltage across the capacitor, when our input voltage is a unit function. It means like it's just basically 0 before 0, and after that it's just gonna be 1. Okay, so this is what we want to do. So first thing we have to do is to find the Laplace transform of our input. What is the Laplace transform of the unity function or a constant? It's 1 over s, because this is 1 also, so this is 1 over s. If it was k times ut, it would be, excuse me, k over s. Okay, and it goes to a system with this transfer function, right? And we want to know what is the capacitor voltage. What is it? It's just basically you multiply the input by the transfer function. So our capacitor voltage is simply 1 over S times 1 over 1 plus S times RC. Okay. Yeah. Now this is our capacitor voltage, but it is in S domain. Okay. How can I find the capacitor voltage in the time domain? It's a little bit challenging because I don't know what's the inverse Laplace transform of this term, right? But if you remember, before the spring break, we saw a concept called partial fraction decomposition, or it's also called partial fraction, what is it? Partial fraction, PFE, partial fraction decomposition, or partial fraction expansion. Okay, so it means that I can write this as something divided by S plus something divided by 1 plus SRC. Okay, why do I do this? Because if I find A, I know how to take inverse Laplace transform of this one. I also know how to take inverse Laplace transform of this one. This is just an exponential. This is just a constant. Okay, so this is why we take PFD. We apply PFD, or partial fraction decomposition. Now, how can I find A and B? Okay, so these two, this term and this term, they're supposed to be equivalent. Like they're supposed to be equal. Okay, so their denominator is of course equal, because the denominator here is S times 1 plus SRC, and it's the same thing here. The numerator for the first one, it's 1. The numerator for this one is A times 1 plus S times ARC. Correct? And plus B times S. Okay, let me simplify this. So I'm just going to write this as A plus, I'm going to factor out S times ARC plus B. So this is the equality that we have. And this equality has to be true and valid for any S, right? Here we don't have any term for S, right? So it means that for this equality to be true all the time, ARC plus B has to be equal. There should be also no S term here. Let me make sure that I'm doing everything correct. Yes. And also the constant term here, it's A. Over here, it's 1. So it basically shows that A, it's going to be equal to 1. Okay. And if I put 1 here, it shows that B, it's going to be equal to negative 1 over RC. Okay. Sorry, is it RC or ARC